So I just want to start by just making a couple of more remarks about that objective stress rate thing. So often in plasticity modeling, we often write or want to use a model that's in terms of the stress rate, and that's because it makes, you know, if you recall, like especially if you have strain rate, if you have a viscoplasticity model where you have a function of strain rate, then you're going to end up with a derivative in the lambda, right? You end up with a differential equation in that lambda that you have to solve for. And so if we work in things in terms of rates, it basically makes ultimately integrating that equation easier. So we often work with rate constitutional models in terms of stress. Okay, so again, you know, like I was in the problem statement and I mentioned before, but just for completeness, to have a valid constituent model, it needs to be one that obeys a rotation, right? So of course, like again, this is just the answer on the first problem in the exam. But if we take the time derivative of both sides of that equation, and we get this. And of course, this is not equal to this. So therefore, this is not objective, is a word we use, or it doesn't obey the principle of material reference frame indifference. And, you know, so a thought experiment would be if we, you know, initially say had axis x and y, and we have a little bar and we're going to pull on it or stress it. Well, that stress will initially only be in the x direction, right? Say we pull on it and we hold it, right? Now, over time, so we're not going to strain it anymore. We're not going to pull on it anymore. So we have a fixed stress. The bar is under stress, and that stress initially is in the x direction, okay? Well, now we're going to begin to do a rigid rotation. So, you know, at time t1, you can imagine our still strained bar looks like that. And then later, at time t2, our bar now has been completely rotated by 90 degrees. And now what was sigma xx is sigma yy, right? Because we you know, again, this is x and y, x and y, right? So we had our bar, we pulled on it, we had a fixed stress, and then we rotated it. Well, again, if you have a, you remember the Cauchy stress lives in the current configuration. So if we rotate the stress, then the stress, which was initially in the x direction, is now in the y direction, right? And so, you know, we need to ensure that we have a constitutive model that can handle that can basically undergo a rigid rotation and not change the stress, because the stress in the sample itself, like if you're sitting in the sample, you know, and imagine you're the bar, right? And somebody pulls on your head and then just rotates you. You're still going to feel like somebody pulling on your head, no matter if they're pulling up or they're pulling sideways, right? So the stress has to remain indifferent to a rotation. So what we often do is we define, a lot of times you'll see this upside down triangle, and we call that an objective stress rate, okay? So understand that triangle, upside down triangle, is a rate. It's like a time derivative, okay? So we often define it as equal to So this is an objective stress rate, and then we have some freedom as to how we choose that omega. Okay? And so if we choose omega to be equal to W, and W is the spin tensor, and we already covered that, but I'll just remind you, if you remember, we had the velocity gradient, and if we take the symmetric part of the symmetric part of the velocity gradient, we get the rate of deformation tensor, and the anti-symmetric part of the velocity gradient is the spin, right? So if we define that as the spin tensor, then this is called the Yaman objective rate of Cauchy stress. It turns out that the Yaman rate under pure shear will oscillate. So it's actually perhaps not the best choice. Okay? So another choice would be to choose it as R from a polar decomposition of the deformation gradient. So we can take the deformation gradient and we can decompose it into a rotation and a stretch. And the decomposition is not necessarily unique. So we can decompose it like this or like this. And in either case, R would be the same, but U and V would be different, right? So this is called the right stretch tensor. This is called the left stretch tensor. And they come from well, the name just comes from where it appears, right, in this equation, right? It's on the right side of the rotation matrix or the left side. Okay. Now, this is a pretty good choice. This is called the green Nagdi rate of Cauchy stress. And this is a good rate. This is one I've often used in computer implementations. It's also known as the co-rotational stress, I guess. However, this, so you might ask, well, if the Yaman rate is known to oscillate under pure shear, why would anyone ever use it? I mean, these days as computers have gotten faster, the excuses are fewer, right? But I mean, the theory behind this has been around for a long time, and there was a time 20 years ago, or 30 years ago, when people were trying to do these computations, and every flop mattered, and so in order to do this this is called a polar decomposition. In order to do this polar decomposition of the deformation gradient, you have to solve an eigenvalue problem. And the eigenvalue problem can be expensive. I mean, you have to do it basically at every integration point in the simulation, which we'll talk about what integration points are real soon when we talk about finite elements. But there's at least one per element. Many times there's more than that. And so it's just, it's expensive. Of course, it's just a 3x3, but you do have to solve an eigenvalue problem. There is an algorithm that we call the Taylor-Flanagan. So all these are just named after the people who wrote the papers, right? Taylor-Flanagan were some fellows at Sandia where I used to work. That basically they have an iterative approach to solve for the left stress tensor So Taylor, I'll just say Taylor-Flanagan algorithm. It's an iterative algorithm to solve for V. And that prevents you, or makes it where you don't have to solve an eigenvalue problem. So you can speed things up a little bit. Then finally, there's the Truesdell rate, which you arrive at by doing a pullback operation. So the Cauchy stress is in the current frame. You pull back to the reference frame, and work through the details, and then you get this Truesdell rate. And all of these rates are objective, so they do obey that kind of rotation.